What's up, everybody? I'm Jason and welcome back to the channel. So this is going to be another slightly technical video, not a usual camera tip, I guess, but we are going to be talking about rolling shutter, how it works, why it's a big deal, what the performance implications are, and so on and so forth. So this is part of a series of videos that I'm going to be looking at that are going to look at rolling shutter performance on the EOS R5 and R5C, and maybe a couple other cameras if I can get my hands on them. And ultimately, I'm doing this video to talk about the bigger picture of rolling shutter performance and testing and my methodology for testing because, well, I kind of hate it when I go to a website and they say, we tested X as Y or whatever, and then nowhere do they have anything about what their methodology is or how they went about testing things or anything like that. You just kind of have to take their word at what they claim it is. So I don't want to do that. I want to put out how I'm testing things. And in fact, I'm going to be going so far as to be putting out a video of how to build the test device that I am actually using. And I will be making all of the source code available for both the test device and the post-processing software that I'm using to do the processing available through a GitHub page. There will be a link in the description. So let's get into this and start talking about why this all matters and how this all works. So I want to start by talking about what the electronic rolling shutter does on a camera. Now, the way you can think about this is as the electrical version of the mechanical shutter that you've had on cameras or that cameras have had basically traditionally. So in a mechanical shuttered camera, there's two shutter curtains. The first curtain opens to begin the exposure. The second curtain closes to end the exposure. Now, the two curtains are obviously physical things, so they don't have infinite acceleration. They can't move instantaneously, and so they move across the frame in some amount of time. Typically, they're very fast, but there is a limit to how fast they actually can be. So the rolling shutter process works somewhat similar, except instead of having a physical curtain moving across the shutter, you have controlled electrical signals that are moving across the sensor or frame. So essentially, instead of a curtain opening, the camera will reset and release. So reset clears the red values in a pixel, releasing it starts that pixel collecting light, so starts the exposure, and then reads out that line of pixels in sequence across the sensor. So based on the exposure time and how fast the camera can actually read out a line of pixels, that in turn determines how many lines the camera can have in flight for a given exposure time. So the faster the rolling shutter performance, or the faster the camera can read out the sensor, the more lines that it can have active at for any given exposure. Now, rolling shutters have traditionally and historically gotten a bad rap, and quite honestly, rightfully so, due to the fact that they have typically had fairly slow readout speeds. In fact, generally, even today, most rolling shutters on cameras have readout speeds that are appreciably worse than the mechanical shutter that they are in some ways replacing. Now, that doesn't have to be the case. Modern technology, stacked sensor architectures, and the incredible amount of bandwidth that you have basically when you don't have to worry about traces and signal integrity and all the fun electrical engineering things that go into communicating over a distance, make it so that we can have incredibly fast readout speeds on our electronic rolling shutters. And so when you look at some modern cameras such as Canon's EOS R3, Nikon's Z9, and Sony's A1, these cameras have rolling shutters that are capable of reading out the sensor fast enough that the mechanical shutter is, in some cases, of secondary importance, or in, for example, the case of the Nikon Z9, simply not even there. So it's not necessarily that a rolling shutter has to be bad. They can be as good or better than a mechanical shutter. Now, the problem that rolling shutters ultimately have caused, or can cause if they're not fast enough, is temporal distortion in your image, and that's ultimately why we care about them. So what happens is because the bottom of the frame or the top of the frame is not being exposed or captured at the same time as the bottom of the frame. You can be very fast, but things can also move very fast. A position of something that moves in the frame while it's being captured will become distorted. So if you pan the camera while the rolling shutter is recording, or while a camera with a slow rolling shutter is recording, the frame will actually kind of lean over. Or if you are videoing or recording something, or photographing even something that's rotating, that has radial elements. So for example, a helicopter rotor blade, or a propeller on an airplane, or the spokes on a wheel on a car, those elements will not be straight radial lines. They will become curved due to this temporal distortion. Now, I should point out that this also happens with mechanical shuttered cameras. However, again, due to the speed of the mechanical shutter compared to the speed of typical rolling shutters, it's not actually as much of an issue as it has historically been in a rolling shutter, electronic rolling shutter system. So that's why rolling shutter testing and performance is so important, and why we need to be concerned about it and talk about it as photographers. So that brings me to talking about how rolling shutter testing is performed. And broadly put, you can categorize all of the rolling shutter testing into three broad categories. You have the whip pan test, you have a mechanical rotating disc or cylinder test, and you have a flickering light test. Now, each of these tests has their pros and cons, so let's talk a little bit about that. The whip pan test, as its name implies, or as it says on the tin, is pretty straightforward. You put your camera on a tripod head and you pan it horizontally very quickly. And you do this while you're recording video, and you look at in the video how much things have been leaned over due to the rolling shutter performance. Now, the whip pan test is what you will find most commonly when you look at reviews of camera gears or demonstrations of rolling shutter performance. It's easy, you don't need any kind of specialized hardware for it, and it gives you a clean visual demonstration of things. Now, that said, there is a time and a place for this kind of test, and there is a time and a place where this test is not especially useful. So where it is good is for familiarizing yourself with your own gear and how fast you can pan things. Where it doesn't work so well is when you're using it as a means to compare cameras. So we could step things up a level and have a more reliable test, and this uses a mechanical moving target, or a motorized moving target. This is what I first ran into when I started looking at rolling shutter performance testing back in the early 2010s, so somewhere around 2012 when I got my 5D Mark III. And it was a test that I actually had run across in a video put out by the Academy of Motion Picture Arts and Sciences, so the people that do the Oscars, when they were starting to look at seriously evaluating how comparable digital cinema cameras would perform for basically Hollywood-level productions. Now, my thinking at the time is, you know, people who are doing directors of photography and cinematographers and directors that are working on Hollywood-level productions, they actually care about this stuff in a level of detail that most of us on YouTube probably don't, or most of us even shooting small kind of like local business video clip segments and things like that. But it also means that they're going to be concerned about doing things in a repeatable and reliable way. And so the process that they put out in their video that they used was to have a rotating disc with radial black and white stripes on it, and a rotating cylinder with axial stripes on it. And these were both motorized, and they'd put a camera in front of it and they would shoot this test. Now, this process is certainly repeatable. The motor should provide the same RPM, whether it's running today or in 9 months. And so you can put a camera in front of a test target like this today, put another one in 9 months, and they will be results should be directly comparable. There's two reasons. As much as I like this test setup, it has this nice visceral quality of being able to be something that you can actually look at it and representative of what the camera is going to actually do. There's two reasons that I ultimately didn't choose to go this route. One has to do with size and one has to do with money. So ultimately, this size target has to be big enough to have a test target and so on and so forth. So typically you're talking about something in the 1 to 4 cubic foot area or volume type range, or something somewhere between a cube 30 to 60 centimeters on a side. That's not exactly small, and if you're not doing something consistently or don't have a large amount of studio and storage space for a test like this, it becomes kind of hard to justify. The other problem is cost. So you are building a test rig with motors and bearings and shafts and rotating targets and so on and so forth, and all of this has to be put into some kind of framework to hold all of it. And that costs money. Now, we're not talking bank-breaking money, but we are talking more than $30 or $40 for the whole thing, especially given the way that prices have gone up on basically everything these days. So I didn't go this route, which brings me to the last option of ways to test for rolling shutter performance, and that is the flickering light test. And basically this takes advantage of the fact that the number of lines that are in flight at any given time while the camera is doing its rolling shutter thing is going to be dictated by the read performance of the sensor and the exposure time. And so if we pulse or strobe a light at a known for a known duration, we can use that to figure out just how fast each line is read out so that the sensor can actually schedule everything and do the work. Now, this test, of course, is repeatable because if you're controlling your lights with a microcontroller or something like that, you can always use the exact same frequency and configuration settings from test to test. But more importantly, it's actually internally consistent. So we don't need to compare two tests using the exact same settings, so a pulse time of 500 microseconds or something like that. We can actually compare tests with different pulse times as long as we know all of the important variables for each test. And in fact, doing that makes things better, because we can work to eliminate errors in our understanding of certain aspects of the process by having a variety of pulse times averaged together into an ultimate number for our performance data. Now, the best way to go about doing this currently, as far as I can tell, is to use LEDs. They have incredibly fast response times, so tens to low hundreds of nanoseconds for white LEDs and single digits to low tens of nanoseconds for direct emission LEDs, so that would be like red or green or blue. This is way faster than the tens to hundreds of microseconds that we would be talking about on the slow side of our performance test. So basically almost an order of magnitude faster than what we are looking at in terms of pulse times. So it's suitable for being able to do this without introducing a tremendous amount of error. Secondly, we can control these LEDs using pulse width modulation. This is typically fairly stable. There's obviously going to be some errors in frequency and whatnot, but not significant errors, like it's not going to drift hundreds of microseconds in a number of shots. But more importantly, it's easy to implement. So pulse width modulation control of various things is built into pretty much all of the hobbyist grade microcontrollers you can find on the market now. So the Arduinos do it, the ESP32s do it, and all of these can be had relatively inexpensively, which is ultimately the things that make it so attractive to me. First of all, it's inexpensive. My whole test light setup cost me less than $40, which actually probably could be done for less than $30. So you're not talking about a huge investment as a photographer who's buying even inexpensive lenses or cameras. Second of all, it's small. My test light is 110 cubic inches in volume, or about 1.8 liters. So definitely small enough to be put in a closet or a drawer or something when it's not being used. Now you could make this as complicated or simple as you wanted to, depending on your skill level or how much time and effort you wanted to invest in it. Mine is purely done off of a breadboard. There's really no soldering necessary or a minimal amount of soldering necessary. So you could do this even if you don't have a soldering iron and soldering iron skills. As the LED strip lights, they make angle connectors for those that you could use to connect up the strip lights. So how does this work and what's going on here? Well, as I said before, the rolling shutter will have a number of lines in flight, because while the exposure is happening, the camera doesn't have to do anything except schedule for the next thing or read out a line that's already been exposed. So if we know the time for the shutter speed and the time of the light pulse, we can look at the frames in the recorded video file and count the number of lines exposed during the pulse. And from that, we can derive the actual time that it would take for the rolling shutter to cover the entire frame. Put simply, the more lines we see in the video frames for the same exposure and light pulse time, the faster the camera is able to read things out and the faster the rolling shutter will be. So this is kind of a graphical representation of what's going on in this whole process. In the vertical axis, we have image lines. In the horizontal axis, we have frame time. The light gray areas are when the pixels in that line are active and exposing. The red areas are when the camera is reading out the information in that line. So the camera will essentially go through and schedule the release of lines in such a way that it can read out a line before it needs to dispatch the next line, and then as it reads out the sensor, it will basically read out the oldest line and dispatch the next line. So if we impulse a strobe of light in the time that the camera is running its rolling shutter, it will not expose some lines at all, or some lines won't pick it up at all because they're not active at that time. Some lines will partially pick it up because they start or end their exposure during the time of the light pulse. And other lines will pick up the entirety of the light pulse because they're fully active, or their exposure time, the light pulse falls within their exposure time. Now I should note this also works for light pulses that are longer than the exposure, just you collect more lines. Ultimately, this process results in a test image that looks something like this. So you have the unexposed lines at the top and the bottom from the lines that weren't active when the light came on at all. You have two partially exposed lines bracketing the two or the four fully exposed lines. And so we can count this and we can say that for this demonstration, the camera sensor recorded 6 lines during its rolling shutter operation. We can then plug that into two pretty simple formulas to calculate the actual timing. So the time for a line is given as the exposure time, or the shutter speed that you're working with, plus the flash duration divided by the number of exposed lines. Now, it took me a little while to convince myself of why all this works out, but ultimately it has to do with the fact that we are capturing, or we are counting, both partially and fully exposed lines in our test image, so that's why we have the 2 times involved here. Once you know how long it takes for the camera to read out a line, it's a simple matter of multiplying that by the total number of lines in the frame to figure out how long it takes the camera to read out the whole frame. So for a 1080p file, you would multiply the line time times 1080, and so on and so forth. Again, you don't have to use standard video resolutions here. This also works for still files and whatever resolution those still files are at, and it would work for raw video that's shot at some non-standard resolution like 5.1 or 5.7K. Now, this whole process actually gives us some really interesting benefits compared to the more visceral mechanical process. So in both cases, we can kind of see whether the camera is downsampling or line skipping, but we can essentially look into what the camera is doing. So if a camera is downsampling, multiple resolutions when you look at the rolling shutter performance will be approximately equal. Now I say approximately equal here because downsampling cameras will seem to have marginally faster rolling shutter speeds at the downsampled resolutions. And this is simply due to the downsampling averaging out various lines. So if you think for about how if you're shooting with an 8K sensor and you're downsampling to 2K, in the 8K image, every 4 lines get averaged into 1 line in the 2K image. So if in the exposure of that 8K frame, 2 of the 4 lines were unexposed and 2 of the 4 lines were partially exposed, when you average that down to the 2K resolution image, basically all 4 of those lines are treated as if they were partially exposed because of the averaging. This will, of course, make the sensor look like it's reading things out slightly faster. However, the error here that you would be looking at is going to be in the order of tens, maybe, or hundreds of microseconds. It's going to be a fairly small percentage of the actual performance. You'll know that, they'll look close enough that you can kind of tell. On the other hand, if your camera is line skipping, say for example the way the R5 does when you go from 8K to 4K standard quality, then you will see a dramatic increase in performance of the rolling shutter in the lower resolution formats. So if the camera at reading out, say 8K was had a rolling shutter performance of around 15 milliseconds, and in 4K it would have a rolling shutter performance of around 8 milliseconds or something in that range, that would indicate that the camera is line skipping for that resolution. On top of this, we can potentially even see differences in processing for different aspect ratios. So Canon's cameras support both UHD and DCI formats, or at least their higher-end cameras do. DCI is a 17:9 aspect ratio, while UHD is a 16:9 aspect ratio. And the way Canon has elected to do this on their cameras is to record the same number of vertical lines, but change how much the width of the image ends up being. So at DCI and the wider aspect ratio, it uses the full width of the sensor. At UHD, it crops off the edges and uses a slightly smaller central crop. We can then look at or make inferences on what kind of processing is being done in that respect with looking at the way the rolling shutter performance is. So if the rolling shutter performance is slightly faster, and again, we're talking possibly microseconds or low microsecond numbers from the using or in the smaller format, that would imply that the camera is windowing because it's reading out fewer pixels per line and therefore can read out the lines slightly faster. Conversely, if the cropped format is showing a slower read speed, that implies some kind of post readout processing being done. So basically digital cropping of each line to be had as it is being read out, or some process very similar to that. So this gives us some interesting insight into what is going on with the camera. So that's the theory part of this. Let's talk about my test setup a little bit and the protocol. Now, as I said before, I am going to have a far more detailed video on how to build a test light like I'm using in both detailed for software and hardware for what's going on. But this is a broad overview of the process. So the core of my test setup is a DIY LED panel. So this is basically take a roll of LED strip lights, cut them down to length, and stick them to some kind of backer, and then throw some diffusion over it so that, or something to diffuse it, to make essentially a light. That is being controlled by an ESP32 microcontroller. This is especially good for this task as one, they're cheap at like $10 or something like that for a development board, and two, the ESP32's LEDC or LED control module has an incredible range of capabilities when it comes to doing pulse width modulated control. Doing the actual toggling is a beefy N-channel MOSFET transistor that is massively overkill for what it's being asked to do, but that also means that it never actually gets hot. Driving all of this on the software side is some software, PWM control software that I wrote. It's probably more complicated. Well, it is more complicated than it technically needs to be because I wanted to be able to interface with this from my computer and make adjustments to frequency and duty cycle and all of that. But technically, if you wanted to put something like this together, you could do this with an Arduino and like 3 or 4 lines of code to control it, or an ESP32, which you can also program with the Arduino's programming and development environment, and 3 or 4 lines of code. The last addition to this entire process, and this was a big lazy addition for me, was an opto-isolator that I added to one of the digital outs on the ESP32, and it's there purely to toggle the camera on and off using the cable release. So the opto-isolator allows me to close, essentially, it works sort of like a virtual button, allows me to close the shutter release contact on the cable release while not actually having the camera and the light and microcontroller electrically tied together. The other half of all of this is the post-processing software. Now, you could certainly process these images manually, bring them into Photoshop or something and count the number of lines that are exposed in any given frame and write that down in a spreadsheet or something like that. However, when you're shooting at 24 frames a second and you're shooting 5 seconds of video, that turns out to be about 120 frames per test image. And I wanted to do this with multiple pulse times per set of tests and then multiple tests for the camera. So different resolutions, different crop factors, using regular recording mode and high frame rate mode, and so on and so forth. So I wrote some software to handle this. Again, like the firmware for the ESP32, I will be making this, or this will be available from my GitHub page. It's written in Python 3 using the OpenCV library. This is pretty easy to get up and running, especially if you're running on Linux, but also if you're running on Mac OS. It's a little bit more challenging on Windows, but it's not actually all that difficult there either. The process basically is as follows in broad strokes. So I iterate through each frame of the video that I've recorded, and I extract the luminance channel from the video files. Now, I can also do this with stills, I should add. Now, if you remember, when you're doing chroma subsampling in video, it doesn't matter what chroma subsampling you actually use. The luminance channel is always full resolution, and since we only care about brightness for this test anyway, there's no reason to worry about anything but the luminance channel. I then calculate a threshold from that image or from each frame to figure out where I need to be to separate the unexposed pixels from the exposed pixels. Now, I don't have the best, most proper, I guess you could say, way of going about doing this. What I'm doing for this is finding the minimum value of the pixels on the frame and then adding 12 to it. And I arrived at this empirically, making a bunch of tests, looking at the resulting test images or resulting outputs, and finding one that wasn't overly subject to noise, but also didn't overly constrain the exposed blocks of lines on the images. So I used that threshold value to to perform a binary thresholding operation on the luminance channel from the image. So all this does is says anything that is a pixel value lower than the threshold value, make it black or 0, and anything that's higher than that, make it white or 255, because we're working with 8-bit scales in the Python. Again, this is another case where 10 bits or 12 bits, it doesn't really make a significant difference. 8 bits is more than adequate for this kind of processing. Once I have a thresholded image, I can do edge detection to find where the threshold, where it changes from black to white or white to black. And then I can do some math to figure out how many lines there are of white in each of the white stripes. Take that for each frame, average it together, and that is the output for the each individual file. Write it out. I ultimately then write it out to a text file so that I can import it into a spreadsheet. So the exact test protocol for when I'm testing things works basically like this. I compose the situation so that the camera is pushed up against the light so that it fills the majority of the frame. Because we're looking at rolling shutter performance, and this is happening at the sensor level, focus is not especially important, aperture is not really important, even ISO is not overly important. What is important is the shutter speed. You want to use a fast shutter speed, so I test at the fastest shutter speed the camera works at. So on the case of the R5, that's a 4,000th of a second. On the case of the R5C, it's a 2,000th of a second. But you could also test at a couple of shutter speeds to further increase the amount of information that you are gaining out of this and minimize error. Once the camera is set up, hooked up to the shutter release on the test light and so on and so forth, I start the procedure where it will shoot 6 5-second video samples for each of, or one for each of my pulse time settings. My pulse times are approximately 65 microseconds, 125 microseconds, 250 microseconds, 500, 1,000, and 2,000 microseconds. Now, the pulse times that I chose here were chosen largely to be a range that covered the fact that my shutter speeds would either be a 4,000th of a second, which is 250 microseconds, or a 2,000th of a second, which is 500 microseconds. So I have a pulse time that's a quarter of each of those and 4 times each of those settings. I then run the files, pull the files off the card, run the files through the post-processing software, take this text file, stick it into Excel, and then average together the various pulse time tests for each of the camera settings that I'm investigating. Now, I do have to admit there are some sources of error in this whole process, and it's worth being aware of them, and these are at least the ones that I've identified. There may be some other ones that I'm not aware of or I haven't cleanly identified yet. The first one is the accuracy of the shutter speed, and this is why I had a video just last week actually talking about how Canon's shutter speeds are not necessarily what they say on the tin. So it appears in summary that Canon, at least, it may apply to other camera companies, but I haven't investigated their cameras, use shutter speeds that are powers of 2 and not necessarily the numbers that you see. So 30 seconds is really 32 seconds, 15 seconds is really 16 seconds, and a 60th of a second really actually appears to be 1/64th of a second. So this kind of appears to apply across the shutter speed range. Now you might be thinking, well, okay, so what? That's not going to be a huge difference. What's the difference between a 4,000th and a 40/96th of a second? Well, that translates to almost 6 microseconds if you do the math to work them out as times. It's also about 2.8%, which is reasonable, a reasonable error in terms of percents. Now, in the testing that I've done, at least preliminarily on my R5, I'm finding that the line read speed is on the order of 3 to 4 microseconds. So a 6 microsecond error in shutter speed would translate to a 3 to 4 or a 1 to 1.5 line error or something in that range, or a 1.5 to 2 line error in terms of how many lines were actually counted. At high shutter speeds, you might only have 60 lines being counted for a fast pulse time, and that's going to introduce a pretty significant amount of error. Now, the way I've gone about minimizing this is using multiple pulse times, and especially having pulse times that are much longer than the exposure time. So the longer the pulse is running to a point, the less the error in the exposure matters when doing the final calculation. Basically, it becomes a much smaller part of the actual resulting number. The other place that I have run into some interesting errors or artifacts is within the line counting part of the post-processing. So ideally and in theory, you would have an image that looked exactly like, or very close to what I demonstrated earlier. It would be black, and then it would turn partially exposed, and then it would be bright, and then it would be partially exposed, and then it would be black again. However, for one reason or another, I find that occasionally I end up with images that have a dark band right next to the edge of the transition. So it kind of goes black, partially exposed, black, partially exposed, fully exposed. Now this doesn't happen on every image, it doesn't happen very consistently, and it doesn't seem to happen terribly often, but it does happen enough that it's going to affect how well the software counts lines. Remember, if you're looking at the lines, it's really easy to say this is where it starts and this is where it stops intuitively, but getting a computer describing that to a computer is a bit trickier. So basically, I have two things that I have approached in dealing with the errors in counting lines. The first one is that I sanity check my numbers. So I will run through the entire video file. I will count all of the frames where I find lines, and then I will look at what the average is of that and the standard deviation, and I will look at and see if there are some crazy outliers. So if I'm averaging 87 lines per frame or per stripe, and all of a sudden I come across a frame that has 20 lines or 500 lines, there's a good chance that that has nothing to do with inaccuracies in the test setup or the camera doing something screwy, and everything to do with the fact that maybe the line was only partially in the test area, so it only counted part of it, or maybe the camera process for some reason counted the black area instead of the white area due to how it broke up in the given image. So extreme outliers I chuck immediately, I don't even worry about working them into the final number. The second error reduction technique is averaging. So when you average a whole bunch of results, you will tend to have a result that converges towards the true value. And that is basically why I want 100 plus frames from each test. So I throw away a handful, I average down the remaining, I don't know, 70 or something like that frames typically into as meaningful of a number as I can get out of it, or as accurate as a number as I can get out of it. So that is the reasoning, the methodology, and the technology behind rolling shutters and rolling shutter testing. As I said, and I'm going to say this again, I'm going to make all of the source code available from my GitHub page, along with the how to build video, which will be coming along shortly. And you'll be able to build this for yourself relatively inexpensively and test your own gear with the essentially the same characteristics or criteria that I'm using for testing mine. So if you found this interesting, let me know by hitting that thumbs up button. If this kind of thing seems like it might be your kind of thing, please consider subscribing if you're not already. And as always, thanks for watching, and I'll see you next time.